Aloha. Today we're talking about water filling Halema'uma'u crater, roadwork on Highway 132, and our Hawaii Island volcanoes. Water continues filling Halema'uma'u crater at the summit of Kilauea volcano, and it's been doing that for about 3 weeks now. And we have images going back to August 1st that really show the progression of this lake, this pond actually, as it's been growing in size as water fills into the crater from the sides. Water has been appearing kind of from the bottom, filling in from below, and it's had this interesting bluish-greenish color, which we believe is due to its sulfates dissolved within the pond. This is kind of similar to what you might see like at a mining quarry.
Right, a geothermal pond.
Something like that, that's right, yeah. So likely it's pretty acidic.
Right.
And it's harder to confirm that until we have a sample retrieved by the USGS-HVO, which they are promising, but logistically there are some challenges to that. So we're curious to know the composition of that lake and its extent, which we also don't know. But the fact that it's been filling in fairly consistently and quickly from below and about a foot a day, something like that.
Right.
Leads us to believe that it's likely coming from the water table. There haven't been that many variations in rainfall over the last month here on Hawaii Island. So we don't think it's one particular rainfall event, but rather moving from the side, right? The competing theory is that there's actually some kind of layer below there water can't drain through and it's just puddling out from above. And that's another thing that sampling the water will give us an idea about, because it's possible to measure the isotopic ratios within the water and get some idea of the rate, the age of that water, how long it's been in the atmosphere, out of the atmosphere, and sitting underground.
Right. So we're going to show a little. We just went through some progression of the lake appearing down there, and you can see this has been images by USGS-HVO. This is a video where they took some thermal images that indicated that the water down there was quite hot, like kettle hot. Down there. That's
right, yeah. 70 degrees Celsius, 160 degrees Fahrenheit is what we're talking about down there. So yeah, this is about the same temperature as we've seen in water that's been drilled down in the Keller well to the southwest of this area. It's our only well in the summit region of the volcano, drilled in the 1970s. And they found water down in there at about the same level as we're seeing it in a pit today. And that water at that level is also very hot, being heated by the magma from below, a long way below that, but the water actually exists from that depth, about halfway back to sea level from here, right, on top of the volcano. So, and it goes all the way down to about a kilometer, a little less than a mile under the sea level.
A huge aquifer.
It's a huge amount of water under there.
Right.
Yeah.
You can see how the surface of the water is turbulent and steams and it's constantly moving. The perimeters of the flow seem to be bubbling, suggesting that it is in fact hot. The one interesting thing is that the Keller well doesn't have a highly acidic nature to it in the samples that have been taken historically.
That's right. So somewhere nearby this pond, there's an interaction of this groundwater with the sulfur that we see in the vents all around there, and that's number one prime suspect for why this pond is appearing to be acidic. But we're awaiting confirmation from a water sample, and of course that's very challenging because the pit is quite deep. The range, the distance, the depth, and the weight of that water, plus the physical characteristics of it, the fact that it is very acidic, that might actually melt through any container you might try to sample it with, make this a very challenging operation, and that's why it hasn't been done yet.
Right. And also there's care about trying to use a drone down there. There's different factors at play that kind of prevent its usage.
That's right, yeah.
And even ideas about using a bucket on a helicopter. It would take a long rope to be able to get down there. And if you were going to try that, you would probably want a pretty big lake, which it's trying to abide. It's coming in about a foot a day.
That's right.
That's a large amount of water, so wait a month and you might just get that water sample.
Yeah, so there's a huge amount of water underneath here. Let's look at the diagram just to show you guys how much water is underneath here based on the Keller well measurements. Let's break out the John Madden pen and show how much water we actually have between the bottom of that crater and the bottom of the well. And that's the top of the water table. And it goes down to the bottom of the well, which we've kind of drawn as the bottom of this diagram at kind of minus 160 meters over to the left. So based on the temperature gradient within the well, they estimated it was actually somewhere around minus 1,000 where the water actually was no longer liquid. And that's how much water can be down there. And why is this important? Because we've been talking about the possible effects of this water on this whole volcanic system. And one thing that it may affect is a release of gas that we're looking for from any magma that's coming into the system. We're not seeing a whole lot of gas at the surface, but we do believe that we're seeing some amount of it coming out. And, we know that the USGS is also examining this possibility and are going to report back on their findings. But the current thinking is that there is not that much sulfur coming out being absorbed by the gas, except locally within that pond itself.
Right. Enough to discolor the pond.
The reason this matters is because what really is going to threaten us, again, what everyone's talking about is interaction of magma with water, right? And we can kind of talk in more detail in the future about how much magma and how much interaction it's going to have and all of that, but what we do know is that as magma comes into an area, it's actually going to be agitating the groundwater, and the water is going to be moving in new pathways. It's going to be hotter. It's going to be steaming more. We're actually going to form more little earthquakes in the ground. We might have things like geysers potentially, or new steam vents opening up that actually track the increase in temperature of water as magma comes into it. We might actually see that pond moving if the ground underneath there is bulging and kind of pushes one side of the pond up more than the other. So we have a lot of different ways that we could now see the change of magma underground without needing things like a tilt meter or a temperature gauge,
Right.
So we're not seeing those signals now. There's there has been an inflation signal in the caldera. There is the INSAR signal showing uplift as well. It's completely possible that the tilt signal, at least, is being influenced by the movement of water into this area. So that's something we want to be wary of as we kind of progress through our update with you guys. But we're not seeing anything beyond that. We're not seeing, any of these hydrothermal earthquakes. We're not seeing changes in the hydrothermal system besides the actual water coming in. The water does not seem to be increasing in temperature, right? And all these things together means that the magma is not coming any closer, and thus why there's no official change in a risk assessment of this volcano at this time.
Right. The volcano officially remains at green/normal, which is the first time since the inception of the system Kilauea has ever been at green normal background levels of activity.
That's right. So amazing times. So moving on to our new segment, grinding the rumor mill. Today our topic involves temperatures measured on Highway 132 roadwork. We start off by talking about the USGS post that discusses their visit to a construction site.
Correct. There was some interesting information that they were able to glean out of that release. One of the main things is that it is still, in fact, hot under some of the deeper areas in the channel once you start cutting into it. Like,
That's
say,
right.
with a bulldozer or an excavator or something along those lines. The lava is a great retainer of heat.
That's right, especially where it's very, very thick.
Right.
And one thing we've learned over studies of Kilauea in the past, going back to Kilauea Iki, everyone talks about, is that the thickness of lava flow dictates to the first order how long it's going to stay hot.
Right.
So Kilauea Iki was 440 feet thick, and that lava flow filling that crater is still hot enough to vaporize water at its core today. Right, even though it's all become solid.
440 feet.
440 feet. So we're talking about areas where the road's being built currently, where we might have up to 80 feet, somewhere like that. A depth of the lava channel is 60, 40, let's call it 40 to 80, somewhere in that range, yeah.
Yeah.
So it's only been a year, so it's still very hot in those areas, but that heat's not going to last 60 years like it did at Kilauea Iki.
Right. And the temperatures that they were able to uncover, the high end was 750 degrees Fahrenheit. And it was interesting in that where they found it is kind of where you would expect to find it. It's in one of the thickest areas where the lava channel crossed the road, the egress of where they cross paths. And it was one of the last areas to have lava, active lava in it to pass through. So it has everything to be the hot spot.
Yeah, exactly. Yeah. Not only was it very thick, but it was also very dense with not a whole lot of gas in it.
Right.
And that is one of the ways that the heat can escape through the pore space of the rock.
Right. And since it was so dense, this rock, that crews have had issues being able to break some of this rock apart, and it's taken some time. And there's been reports, even USGS reports, about drill bits turning purple, which is something that just happens when you start beating on really dense rock, especially if your drill bit isn't, brand new.
That's right. So that was the original report with USGS. And since we're addressing rumor mill right now, what was the rumor that was put out in response to that report? Right.
So the rumor is that the drill bit turned purple because of the heat of the lava, which is an interesting misconception, but a really big misconception for many different reasons. Like, one, the lava, once it comes out of the ground, once you rip the ground out and you expose this hot rock, it's 750 when you expose it. And then it's rapidly going to cool.
Yeah.
Right? So it's rapidly going to cool. You're not going to heat a piece of metal. Even by smothering it under that rock, it's not going to heat up to 750 to be able to temper it. But the other issue was just the insinuation that the entire lava field is 750 degrees.
That's right. When we look at the thickness map, we can show you guys where it was the thickest, is where these hottest temperatures are being found, and that was expected. Dense rock, right where we cross the channel, all those spots would have been spots that were circled immediately off the first survey map.
Right.
Reconstructing this road. And this is exactly the problem spots right now.
Right, and it's not at the surface. At the surface, there are spots that do vent some hot air, but those are not this hot, 750 degrees now. These spots have been ripped. They dug into the lava, exposing the layers beneath it like an onion, just peeling them away. Each layer you peel, it gets hotter.
Right.
So that's where these temperatures are coming from, is in these areas that have been peeled very recently.
Right. Let's look at our thickness map. And here you can see the areas that are green are where the flow is the thinnest, and the greens range all the way up to about 50 feet. And then the very lightest green, almost yellow, goes between 50 and 66 feet, and the yellow, 66 to 82. So you can kind of see the edges of the channel. We're going to John Madden it up again here.
Yep.
The edges of the channel right there are the ones that are actually the most yellow, right? There's a little flatter spot where the pen just stopped right there. But now let's draw on there a trace of the road across these flows, right? So we went across some greens, a little bit of yellow there, but...
That's not a great trace, but it'll do.
Right? Yeah, and the area that's circle right where the hot spot is, right in there, right, is because of that really yellow area. So,
right,
that's area was very thickest. And you kind of see that going downhill from there. It just gets worse and worse, getting all the way to the offshore parts being extremely thick and red.
Right, and for those that can't see the channel all the way down, at the very end of the eruption, it basically did that.
Yeah.
And then down here, it's kind of a mess.
Our final segment today is our volcanoes update.
That's right. We're going to start with the higher priority level, according to USGS, Mauna Loa.
That's right. Mauna Loa is still showing a bunch of earthquakes every week. Those earthquakes are still elevated beyond background levels, but they are not accelerating at an alarming rate. They are still at an elevated rate that we're watching, but is not showing very much change over the last few weeks.
Right. And you might not be able to see this in the USGS-HVO earthquake map. This map here is showing all earthquakes within the last 7 days, and it doesn't show a lot of activity in Mauna Loa.
That's right. But that map only shows earthquakes larger than a certain magnitude.
Right.
And when you look at the actual map on the deformation page on the USGS site, which we're looking at right here for the last 5 years, you could also see that over larger periods of time, the increase is actually fairly consistent. So let's point out that increase here at the right end of this graph with our magic pen. There it is, right? So that's still increasing. And one of the challenges we have is that we as humans operate on the solar daily cycle, and earthquakes may not actually, average out in time over 24-hour periods of time. So when we look at the daily earthquake counts or weekly earthquake counts, those can be occasionally good indicators. But you might have a week that's slightly lower, a week that's slightly higher, a day that's slightly lower, a day that's slightly higher. And that's not of that much concern because you really have to average it out over longer, several weeks at a time, like this plot right here is doing.
Right. And you can see that general uplift, and you can see during 2014 to 2017, it was considered a period of elevated unrest on Mauna Loa. And that was partially due to the earthquake activity, but also due to the inflation that was seen there.
The GPS line.
The GPS line, correct.
Yeah.
So, but you can see this earthquake kind of thing is a little lower. But this over here is kind of more on the consistent side. It's a lot of back and forth, but this one trend is kind of a pronounced trend.
Right. For you guys that are watching Dana Squiggles, and he always likes his little squiggle at the end, you can pick your squiggle of the week and let us know here at the end of the video which one you like the best. So let's go down and look at the GPS plots on this same page here, just so we can kind of round out the Mauna Loa. And we can see that we have an increased still rate of spreading across the summit of Mauna Loa that you can see at the right end of that upper plot right there. Yeah, right in there. But it hasn't really changed over the last couple months either, right? It's just kind of the same pattern we're seeing. Elevated, but not to the point where we're worried about another alert level quite yet. First, we need to see an increasing pattern of erupting activity.
Right, and you can see the eruption 2018 would be there-ish, maybe a little bit over here,
corresponding to that flattish spot right above to the right of that.
And that was when USGS lowered Mauna Loa to green. So this is the green area.
Yeah.
And then we get back into inflationary, and now we're back into yellow.
Great. So that's basically it. At this stage of Mauna Loa's activity, the tilt isn't that useful. Maybe we can take a quick look at it just so you can understand what the tilt looks like when nothing is actually happening. Because someday it may look a little different, and that's what we'll be looking at. So you can kind of see that on our summit tilt for the last week or month is just kind of showing our daily cycles up and down. It's kind of more or less showing a flat range, and you can see the scale that's being outlined right there is kind of showing more or less 0.8 down, 0.8 up microradians. So not a very large scale at all.
Yeah, it's a very small scale here, and that's supposed to be a 2. Don't laugh.
All right, so not a whole lot happening in Mauna Loa. So now we transition to Kilauea and the 2 felt earthquakes that people experienced this past week. The first one was on Kilauea. The second one we'll talk about a little later. But the first one was this 3.7. It happened on Saturday, August 10th. It was about 5 miles down. And it was a typical South Flank earthquake. So the South Flank is still moving. We are not seeing any changes of that on any of Kilauea's monitors. But that was an earthquake that was felt island-wide.
Right.
While we're on earthquakes, let's talk about the second earthquake that people experienced this past week, which was a few days afterwards. And that one was actually just in the middle of Hilo Bay over here. A 4.5. It's been revised down at 26 miles down.
There we go. That makes more sense to me. Yeah, the 10 miles down.
It was an initial estimate.
It was an initial estimate, and it didn't jibe really well.
Right. So that makes more sense. There have been earthquakes in this area before. Most notably, in April 1973, there was a 6.2 near here that caused a good amount of damage near Halema'uma'u. So, do
you want to describe just a brief process of why these quakes happen, these flex quakes?
Yeah, it's it's essentially the weight of the island adjusting as it moves away from the hotspot. So as islands over the hotspot, it absorbs heat and it's being built higher and it kind of sits high over top of that area of heat, not unlike a strip of metal going over a Bunsen burner, if any of you guys have done that experiment in any part of your school. But when it comes off of that area, it starts cooling, contracting, sinking back into the ocean, and generally settling. And because a volcano is a layer of lots of lava flows that are basically like a giant stack of magazines, those layers, as they are pushed up or down, they kind of slide back and forth across each other. And that's what actually causes those earthquakes deep down at the base of the volcano.
All right. And you can see just how the hot spot has moved over millions and millions of years.
Yeah, that's right. Yeah. So that's the topic for a different day. But yeah, we have a progression of older islands to the northwest and the youngest and active one to the southeast. So this trend has been happening in Hawaii for on the order of 80 million to 100 million years.
Right.
So yeah, the last thing to look at is our Kilauea monitoring data. And we can look just at the two main plots, the month-long plot of the summit and Pu'o'o, which Pu'o'o actually went out last week and hasn't come back online, or maybe it came back online briefly, but it's back offline again.
Yeah, it's kind of in a bad spot right now.
Yeah, you can see there's a very straight line as a data gap in between there, right? There's a data gap from here to here. So that station is essentially offline. The summit station is showing changes in the order of plus or minus 1 microradian, looks like. Like the deflation inflation cycles are more in order of half microradian.
Which it looks like we have one.
Yeah, that we've just been coming out of, yeah. So that's interesting. But there's nothing really alarming happening there. And once again, we might be in a phase where the tilt isn't as meaningful because of the possible effect of water coming into the area. So if we rely then more so on the GPS, we can see that its pattern hasn't changed that much recently.
Right. Sorry, I was playing with water.
If we look at the GPS, we can see that the rate of change isn't any different over the past few months.
Yep, pretty much the same.
So the caldera is still spreading apart. That's some combination of the south flank still moving, the southern wall of the caldera moving, and some effect of the magma coming in to some unknown depth down there, or possibly moving around. It's not clear how much of that is magma, or where that magma is actually coming from. But all in all, the signals are not conclusive for any magma. You definitely have to agree with that. And so with that concludes our 3-part update. Thanks for tuning in, you guys. Mahalo and aloha.
Aloha.